Okay, so as we introduced before, we will separate 3 steps to learn about PDE. So the first step is from the physics model to drive our mathematics PDE, and we already did from 1D metal rod heat transfer to generate our 1D heat equations. And we know what kind of common boundary type of boundary conditions. Then the second step is trying to solve the PDE. So the second step is solve PDE. Basically, we want to ask this PDE UT equals to alpha squared. UXX, as we mentioned, this alpha square is actually the effective heat transfer. Effective thermal conductivity. And we can trying to ask the question is what temperature look like at infinite time. Basically is in equilibrium distribution. What equilibrium means, what is at infinite time? That means my UT, so the temperature is not as function of time anymore. That means my UT is equals to 0. So from UT equals to 0, what we get? We get UXX equals to 0. Then what this equation is actually our 1D Laplace equations. So 1D Laplace equations. Okay, then we are trying to solve this 1D Laplace equations using different boundary conditions. Okay, different boundary conditions. And what kind of boundary conditions we saw before? One common boundary condition is fixed temperature. So it is fixed temperature. And how I give this fixed temperature, since it's already now as function of time, then we say U at 0. So temperature at the initial end of initial point of the rod is equals to U left. UL is at the ends of the rod is equals to UR. Okay. Then my UXX is the partial differential equation. UXX equals to 0. Then what kind of UX should be? So the first derivative of X should be some constant. Then my U should be C1X plus C2. Okay, so that is our temperature distribution as function of X, Okay. Then let's put our boundary conditions in and see what is our C1 and C2 equals to, right? So when I have U naught equals to UL, so U naught is equals to C2 is equals to UL. So that is our constant. Second constant is UL. UL should be equals to C1 times L plus C2, which is UL, equals to UR, okay, the right-hand side of the temperature. So my C1 will be equals to UR minus UL divided by L, okay? So the temperature difference between the left-hand side and the right-hand side divided by L is the constant C1. Then our final distribution of the rod will be UX is equals to C1, which is UR minus UL divided by LX plus C2, which is UL. And you know this UR and UL are fixed temperature. That means they are fixed value and divided by L. This will be a slope of this UX function, and this slope is constant. So you can imagine the rod temperature will look like at infinite temperature at equilibrium will look like something like that with a constant slope. So we can say this is A, this is B, okay? Then the second part, second type of the common boundary condition is isolated. Isolated. Insulated. That means the gradient of the temperature at the initial and end point of the rod, the gradient of temperature should be equals to 0. So that means my Ux at 0 at all time equals to 0. Ux at the end of the rod Lt equals to 0. That is our insulated boundary conditions. Then what we have Uxx equals to 0. That is our partial differential equations. We should get the same equation Ux equals to C1x plus C2 because Ux will be equals to C1. Then the U as function of x should be C1x plus C2. Let's put those boundary conditions in to get what is our C1, what is our C2. So Ux at 0 will be equals to, so Ux should be equals to C1, right? So Ux at 0 equals to C1 equals to 0. Well, UXL equals to C1 is 0. So those boundary conditions give you that C1 constant equals to 0. Then how about our C2? In the end, the C1 equals to 0, then my function of temperature as function of x should be equals to Ux should be equals to C2 is a constant temperature. So at the infinite time in equilibrium state of this metal rod, the temperature distribution should be constant when your tip of the rod is insulated. And that makes sense because the tip is insulated, there is no heat transfer through the tip. Then the temperature inside the rod should be just distributed evenly in the end as time is infinite. And the C2 is not arbitrary. It should be really depends on the tip of your temperature at initial point and the final point. The average out those temperature. It should be, you probably will have some initial conditions where the initial condition is the temperature through the rod at initial time. And those are the temperature distribution. Okay, at T equals to 0, this is the temperature distribution. Then in the end, you C2 should be equals to distribution out all the temperature at infinite time. So the C2 should be equals to the average out from 0 to L. Ux0 means at time equals to 0, the temperature distribution, average out. The integral then is averaged by the L, should be the C2, which is the final temperature. In the end, should be constant. So this is two simple type of the boundary condition: fixed temperature and the insulated temperature at the tip for the rod, and how we can get the distribution of the temperature at infinite time through these Laplace equations as well as those simple boundary conditions.